In this video, we're going to go over exam 2 review, the solutions that are posted online. Question 1 is asked to compute the torsional shear stress in a titanium tube that is 1200 millimeters long with a diameter of 90 millimeters when subjected to a torque of 25 kilonewton meters. I also want to determine the angle of twist. So for these problems, the main equation is this tau max equals Tc over J. This is the maximum torsional shear stress, where T is the torsion, C is the distance from the center to the outer edge of the cylinder, which in this case is the radius, and J is the polar moment of inertia. First, we need to get the polar moment of inertia using the equation for a circle, which is pi d to the fourth over 32. We know the diameter is 90 millimeters, so pi times 90 millimeters up to the fourth divided by 32 equals 6.44 times 10 to the sixth millimeters to the fourth. I also need to obtain C, which I just said is half of the diameter, which is 90 millimeters divided by 2 equals 45 millimeters. Now we need to plug everything into this equation and maintain consistent units. First off, the torque is given as 25,000 Newton meters or kilonewton meters. So I've written 25,000 Newton meters. The C also needs to be in meters. Over here I've answered in millimeters. I converted that to 0.045 meters. J was obtained in millimeters to the fourth. It needs to be converted to meters to the fourth, so we have consistent units. I take 6.44 times 10 to the 6th, multiply it by 1 over 1,000 to the fourth power. I get 6.44 times 10 to the negative 6. As I pointed out in the last class, there's a trick. If we have the answer in to the 6th power, it becomes the same exact value before the times 10, 6.44, but times 10 to the negative 6. That only works if you already have this into the 6th power by just simply putting a negative in front of that. But it's always best to just convert it and confirm that it works out this way. I plug all this into the calculator. I get 174, 689, 440 Newton per meters squared, which is a Pascal. Then I'll write that as 174 megapascals, or 174.6, 174.7, something like that. Okay, I have obtained the first answer. I also ask for the angle of twist. The angle of twist equation is theta is equal to TL over GJ, or JG, whatever, any variation of that. So T we already have is 25,000 Newton meters. The length up here is given as 1,200 millimeters, which it needs to have consistent units in here as well, which is 1.2 meters. G needs to be obtained from a table, which is on this page. So that is the shear modulus. Okay, and I tell you what type of material it is. It is a titanium tube. So I go to this table and search for titanium tube. Well, titanium alloy as the material. Okay, and I see 43. I see 43, but it is in gigapascals here. Okay, so I choose gigapascals because I am using newtons and meters. I'm using I'm using SI units, so I need to use the gigapascals, but I needed to not just write 43. I need to write 43 times 10 to the 9th, because that is what a giga is for an individual Pascal. Then I need to write the J, which I've already have up here, but maintaining millimeters to the fourth as well. I have that all written in, and I plug this into my calculator. I've independently calculated the numerator and the denominator, and then determined that it's 0.108. That is radians. This equation always pops out in radians. However, I want the answer for angles of twist in degrees. Well, we need to convert radians to degrees by multiplying by 180 degrees over 1 pi radian. That gives me 6.2 degrees for my angle of twist on this tube with this information provided. Okay, that is it for this type of problem. Okay, the tables will always be provided in exams or homeworks. Now, question 2, similar. It's a 2017 Corvette Z06, has about 650 horsepower, which rotates the drive shaft at 5,100 revolutions per minute or RPMs. First, I want to know what the torque is in the drive shaft. Once you've obtained that, then I want to know what the maximum torsional shear stress in the drive shaft if the drive shaft has an inside diameter of 2 inches and an outside diameter of 4 inches. So it is a hollow drive shaft. So there's a circle with another circle missing inside of it, like a donut. And then I also want to know what the angle of twist in the drive shaft is if it's 4 feet long. So first, we need to write all of our information out here. So the power is 650 horsepower. Okay. The rotational speed, capital N, is 5,100 revolutions per minute. I've written that down. The outside diameter is 4 inches. The inside diameter is 2 inches. If I'm going to obtain the maximum torsional shear stress, I need to get C, which is the outside diameter divided by 2. So I took 4 inches divided by 2 and obtained 2 inches for C. Then I need to obtain the torque. Now there's two equations to obtain the torque depending on which unit system you are working in. This problem is in US unit systems. We can see the inches here. So therefore I need to use this equation. The power is equal to Tn over 63,000. 63,000 is a conversion factor. I could rework this equation to solve for torque because I want torque. I have the power and I have the rotational speed. So I rearrange the equation so T equals P times 63,000 over N. Well, I have this information. I put this in 650 horsepower times 63,000 divided by 5,100 revolutions per minute. Plug this in the calculator. I get 8,029 pound inches. This equation will always pop out in pound inches. If I want to see what that is in pound feet, then I convert that 669 pound feet. I've merely done this conversion here to show what the torque is in a Z06, which is similar to usually what the horsepower is. Okay, I also need to obtain the polar moment of inertia for a hollow cylinder now, which is, the equation for this is pi times the outer diameter to the fourth power minus the inner diameter to the fourth power. Remember that these need to be individually raised to the fourth power, not subtracted and then raised to the fourth power. It's a different number. So ensure you do that, and that's divided by 32. So I plug those values in and I've obtained 23.56 inches to the fourth. Now with all that information, I can go into the same equation we used previously, that tau max is equal to Tc over J. The torque that we have previously in pound inches, we need to maintain this one because we have inches for everything else. So it's 8,029 pound inches multiplied by C of 2 divided by J of 23.56 inches to the fourth. We have consistent units. We get a maximum torsional shear stress of 681.53 psi. Okay, and so on the solutions I ran out of space to determine what the angle of twist is, but it's the same problem as this, theta TL over GJ. You also need to maintain use the specific G that's provided depending on the material, which I believe actually wasn't given in this problem, so we won't worry about calculating that. Okay, so question 3 is draw the shear moment of the below beam. Okay, we ignore the weight of the beam. We've always ignored the weight of the beam in this class. So here's the beam. It's a simply supported beam with a pin and roller on each side. It has a 25 kilonewton load here at 25 meters away from this pin. 50 meters away from that is 50 kilonewton load downwards, and then the roller on this side. The first thing you need to do is obtain the reactions right here, which I already have answered. I've obtained that answer, which is farther down the page. I have some moments at A, assuming the first left pin is A, which is equal to a negative 25 times 25. This is this distance right here. It's the difference between 175 minus 50 times 75 plus by times 100. So by is equal to the 43.75. Then I have some forces in the y direction, which is the negative 25 force minus the 50 force plus by, which I've just obtained, plus the unknown ay is equal to 31.25. With those both obtained, I've written them in here. Then I will draw the lines for every load. So there's the load here, 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 below the beam. Then I know I will label this. First I will label this is the shear diagram with a V, with this being the 0 line, and I'll write the units here. Same thing with M. This is the M line, which is 0 for moment, and kilonewton meters for my units. Now, first, I go upwards right here due to this 31.25 kilonewtons load. So I could start at 0, go upwards to 31.25 kilonewtons. Okay, then the next rule says in between point loads, the shear must remain constant, so I've drawn a horizontal line until this next boundary. At this boundary, I will subtract 25 kilonewtons from the 31.25, which I obtained 6.25. Okay, that math isn't written on this page, but I've just done that in my calculator. 31.25 minus 25 is equal to 6.25. So I've obtained that magnitude. There's a constant load in between, a constant shear in between these two loads. So I've reached this point. Now from here, there's a downwards force it's causing a shear at this location. So it's 6.25 minus 50 equals negative 43.75. Now I'm constant between point loads. I've reached this point. And then to get here, there's an upwards force, which is a negative 43.75 plus 43.75 equals 0. So my shear diagram closes out, and I'm done with shear. Okay, then I move on to my moment. So first I need to know the rules of what type of line connects. So if there is a square shear on the positive side, it is an upward slope line. So square shear, upward slope line, square shear, upward slope line. Negative shear that is square, so a downward slope line. So that's the type of lines. Well, what are their magnitudes? Well, the magnitude for here is just simply the area of this square. So it's 31.25 kilonewtons times the distance it acts over, which is 25. So 31.25 times 2.5 is 781.25, which is kilonewton meters, which is this point. Okay, well then this area right here needs to be then added to 781.25 to get this number. So that's what I've done here. 781.25 plus 6.25 times 50 is equal to 1093.75. That's where I've obtained this number. Then I need to continue to add the areas. So I have 1093.75 plus the negative 43.75 times the distance acted over is 25. Do that math, I get 0, and it closes out. And I've completed my moment diagram. Now you need to ensure that these lines have the same slope from here to here, so that when it transitions from this space to this space, the same slope is transitioned. So it's a consistent moment. Okay, that's how I did the moment diagram for this problem. Now here's a new problem. Draw the shear moment diagram of the below beam, again ignoring the weight of the beam. So first let's just look at the beam and ignore some of the solutions that are already here. This is a beam that's affixed to the wall. Okay, so there is a known moment here, and there's an upwards AY force. It has a constant distributed load across the top at 165 pounds per feet. There's a force right here applied upwards. It's given as 4,500 pounds. It's 49 feet away from AB, and actually the total distance is 54 feet. The entire length of the beam is 54 feet. So the first thing I need to do is I need to turn this distributed load into an equivalent resultant force, which is just the magnitude of the distributed load, 165 pound-feet, multiplied the distance it acts over. The total distance it acts over is 54 feet. I get 8,910 pounds. Okay, that acts in the middle when it's a constant distributed load, which is just 54 divided by 2, which equals 27. Okay, once I've obtained that, then I need to determine what MA and AY is, which I've done here below at the bottom. I sum the moments at MA, that equals 0. When this type of problem has a moment in it, you include the moment here, MA, which is in the positive direction. I assumed it to go this way. I assumed it to go counterclockwise, so it appears positive in the equation. Minus the 8,910 pounds, which we just attained, that acts at a distance of 27 feet from A, plus this 4,500 pounds that acts 49 feet away. So that's where I get the 49 feet. I do this math, I've obtained a positive 20,070 pound-feet. This is the magnitude for MA. It is positive, therefore my assumption is correct that it goes counterclockwise. So that's where I've written in the answer here, 20,070 pound-feet. Now I need to get AY. AY is equal to AY, similar forces in the Y, has AY minus 8,910 pounds from the resultant force, plus the 4,500 pounds at the end. AY gets a positive 4,410 pounds, which means it goes upward. I've assumed correctly, and so I've written that answer in. Okay, now with that information obtained, I will draw the lines downwards. Okay, there's 3 of them. Okay, one at this edge, one at this force, and one at the other edge of the beam. I've drawn the horizontal line to mark my shear, which is my 0 line, and put my units in pounds. Same thing with M, 0 line, and in pound feet now. Okay, so the first thing, there is an upwards force right here at the edge, which causes an upward jump in the shear diagram of 4,410 pounds. Okay, but then immediately the distributed load takes over. So over here at, I'm calling at shear location 2, which would be all the way over here, is the 4,410 where we left off, minus the magnitude of the distributed load, which is 165 pound per feet, multiplied by 49, not by 54, because I'm just only getting the magnitude of it at this point. So I only take up to that point, which is 49 feet. I do that math and I get a negative 3,675 pounds. Okay, negative 3,675 pounds. Okay, I'm maintaining to work in pounds instead of kips in here because you'll see that rounding will start to affect it. So I maintain just pounds. Okay, so I've gotten that value. Okay, but then I continue. There's still distributed load in between this last distance right here of 5 feet. So the shear at location 3, we need to first deal with this force right here. There's a force, so it's negative 3,675 pounds plus the upward concentrated force of 4,500 is equal to 825. So there's a jump in the shear diagram, which all concentrated loads do. So I maintain that jump. Then after that, there's still the distributed force, which I was talking about previously, which I take off where I was left off, 825, minus still the distributed force magnitude, 165 pound-feet, but just now times the remaining distance of 5 feet. That gets me 0, and we've closed out. Okay, notice that the slope of this line that I've drawn here is the exact same slope of this line right here. So without this concentrated load, this would have just kept on going. But the constant load caused a shear, and it still kept on going at the same slope because the distributed load right here is consistent. It doesn't change. So the slope of this shear diagram should not change. Okay, it just got cut and shifted up, and they maintained the same slope. Okay, so that's the shear diagram. It closed out and we got 0. Now, for the moment diagram. The first thing we need to do with the moment diagram is it still starts at 0. Just like the shear diagram starts here at 0, but then on the line it shifts upward. M still starts at 0, but there's a shift because there's an applied moment. Applied moments cause shift in the moment diagrams, like applied concentrated loads cause shifts in the shear diagram. So we went over this in class. A counterclockwise applied moment causes a downward shift in the moment diagram, and a clockwise applied moment causes an upward shift in the moment diagram. So this is counterclockwise, causes a downward shift of its magnitude, so it starts at 0, drops immediately down to negative 20,070 pound-feet. Okay, after that, then we need to look at the area of this triangle to get the magnitude. Okay, the type of line for a downward distributed load is a downward opening parabolic diagram. So that's why this line is going to be a curved up to some point. Well, how do we get that point? Well, we need to use similar triangles to determine this distance x here that's written in green. So the way that we do that is notice that there's 2 triangles on top of each other. The first one has a height of 4,410, which I've done over here, over a distance of x, which we don't know. That is the base of that triangle. Well, there's another triangle that goes all the way down to here and over. So that is 4,400 plus the 3,675. Not plus a minus, it's just the distance from here to here, which is always a positive measurement. So I add those 2 together over the distance they act over, which is the total distance here, 49. So I've written that out, and I've done the math. This says, therefore, x must equal to 26.73. You do this in your calculator, and you're going to get 26.737373 repeating forever. Because of this, like repeating like forever, the final answer is going to not be all nice and 0 on the moment diagram. I'll explain later in the math, but because this carries on forever, depending on where you cut this off and round it, like I've done here, 0.73, it's not going to close out all nice, but it's fine in this case, and I'll talk more about it momentarily. But I've just cut it off at 26.73 feet. Okay, then I'll maintain this number throughout. Okay, so then now at moment location 2, which is this value, I've started where I left off, negative 20,070 pound-feet, plus this area, which is a triangle. So 1/2 the height of 4,410 times that distance I just obtained. 26.73. That equals 38,869.7 pound-feet. So that is that value. Okay, notice the slope right here. Okay, it's a little pointy because I'm not the best artist, but it should be 0 because it crosses the 0 line right here. Okay, so the slope right here is real high, and then it goes to 0 because the values right here correspond to the slope of the lines here. So this is a 0 slope right there at 38,869.7. Okay, then to get the next value at this point is to continue where we left off, plus this area of this triangle. So I was at 38,869.7 pound-feet, plus 1/2 of negative 3,675 pounds times the distance. Okay, the remaining distance here from between the 49 is 22.27. I got this by subtracting 49 from 26.73. Okay, I get 22.27 is the remaining distance, this distance right here. Okay, and then I get a negative 2,051.4 pound-feet. So it goes back into the negative down here. Okay, then the next bit is to add this little area of this little triangle. So I was at negative 2,051.4 pound-feet plus 1/2 the triangle times its height is 825 pounds times the last little distance right here is 5 feet. Okay, I do that, and actually this is where I was talking about. I will not get 0, I'll get 11. Okay, but 11 in comparison to numbers that are in the 20,000, 38,000, 2,000 is basically 0, and it works out that way primarily just due to the rounding. If you actually, you plug this in your calculator and you get this carried out, if you carry out that long 73737373 for like 10 decimal points or whatever, you will get this number to be even smaller. The further you carry this out, the smaller this number will actually get. Okay, the best way to do it is when you first do this calculation right here, do it as far as you can, you'll get 38,860. Then from there, if you keep on working, it'll close out to be 0. So this is fine to basically close out to 0. Okay, then that's how we do that. Notice it's still distributed load, so we still have a concave opening downwards parabola down here, not a triangle, so always concave down still. Okay, that is it for this problem. Okay, the next problem is to determine the location of the centroid from this x-axis with y bar and the moment of inertia with respect to the x-axis of the below shape. Okay, so it's a square with a missing square inside it, okay, with the proper dimensions. So the first things we need to do is get the areas and the y squiggles for the individual areas. So the area, we'll call the big rectangle, is just 12 times 6, which is 72. Area of the small rectangle is 4 times 10, which is 40 inches squared. The total area is just the difference between the two. 72 minus 40 is equal to 32. Okay, now the y squiggles of the big rectangle. Big rectangle has a height of 12 inches. The centroid acts in the middle of that, which is 12 inches divided by 2 equals 6. Okay, y squiggle for the small rectangle is 1. This distance from here to here is 1. Distance from here to here is 1. So that is 1 plus 10 divided by 2, which gives me 6. Okay, so in class I pointed out that if the y squiggles are the same, then the overall y bar is going to be the same, which we can see here, but just going through the math for homeworks and exam, y bar is a br times y squiggle br minus a sr, the areas times the squiggle divided by the total area, which is 72 times 6 minus 40 times 6 divided by 32, which does confirm 6 as the overall centroid. Okay, so then now I've got that answer. The next bit is to do the moment of inertia about the x-axis for the big rectangle and the small rectangle, and then subtract them for our total. Okay, the formula for the rectangle for moment of inertia is base height cubed over 12, which is 6 12 to the third power divided by 12 for big rectangle gets us 864 inches to the fourth. Small rectangle is 4 inches times 10 cubed over 12, which gives me 333.3 inches to the fourth. Okay, notice I do not need the parallel axis theorem because their individual y squiggles line up with the y bar. Okay, so if you use the parallel axis theorem, it would just be 6 minus 6, which is 0 squared times the distance, so that part of the equation goes to 0 and goes away. So I just subtract these values now. 864 minus 333 is 530 for my overall moment of inertia about the x-axis for this shape. That's it. Okay, then there's another last problem. It's an I-shaped beam. Okay, there's two ways you could determine the moment of inertia about this. So you could do a big rectangle minus these individual rectangles. That works too. Or you could do a way I've done it by dividing area 1 right here, the little circle, and area 2, the middle, and area 3. So area 1 is equal to area 3. We noticed that they're symmetrical, that the flange, this part, and this part of the beam are the same. So area 1 is equal to area 3, which is just 6 inches by 1 inch, which is a 6 inch squared. Area 2 is 8 inches by 1 inch, which is 8 inches squared. So the total area is 2 times the 6, because there's 2 of them, plus 8 equals 20. Okay, y squiggle for the part 1, measured from this x, is 1 inch plus 8 inches plus half of 1 inch, which is just a half, gives me 9.5. For y2 is 1 inch plus half of 8, which is 4, which gives me 5. And then for y3, it's just half of an inch. So then I plug all those in, keeping them consistent. 6 times the 9.5 plus 8 times the 5 plus the 20 times the 0.5, all divided by the total area. Okay, my mouse movements a little while ago were off because there's 6 inches squared times 9.5 times the 8 inches times 5 inches times the 6 inches by 5 inches. All that divided by the 20. That equals 5. Okay, you can kind of see it's symmetrical, so it should be right here in the middle of 1 inch divided 1 inch plus 4 inches divided by 2. 8 inches divided by 2, sorry, equals 4 plus 1 is 5. Okay, so then now I need to get the moment of inertia. Moment of inertia for part 1 and part 3 are the same, and you do need the parallel axis theorem because notice that their individual y squiggles are not the same number as the overall y bar. So first I do base height cubed divided by 12, so 6 inches times 1 inch to the third power over 12 plus their area, both of their areas are 6 inches, plus, or multiplied by 9.5 minus 5. Okay, 9.5 minus 5 squared. Okay, but there might be a question of, okay, well, this is for I1. I1 is 9.5 minus 5. But for I3 should be 5 minus 0.5. Okay, well, 5 minus 0.5 is 4.5, and 9.5 minus 5 is also 4.5, so it works out because it is symmetrical. Okay, and so I've known that because it's symmetrical. If you're not 100% sure, just do them individually. That is totally fine. But that works out to be the same number, so that squared, everything multiplied out, is going to equal 122 inches to the fourth. Okay, but then the middle part is different. The middle part, its y squiggle is the same number as y bar, so I don't need the parallel axis theorem portion. So it's just base height cubed over 12. Its base is 1 inch times 8 inches height cubed divided by 12 is 42.66. Then I just add these all up. Okay, 122 plus 42.66 plus 122 again equals 286.66 inches. Okay, it's important in both of these problems to follow along, make sure you know how to get the individual y bars, and to know when to use the parallel axis theorem. I realize both these problems are nice and convenient, where each portions are all sharing some part of the overall y bar, but that may not always be the case. So just go through and follow and know how to solve these problems. Okay, that is it for this video.